In the early 1900s, scientists discovered that light previously thought to be only a wave also behaved like particles called photons. Einstein's photoelectric effect. This dual nature raised a bold question: could particles such as electrons also have wave properties? In 1924, the French physicist Louis de Broglie proposed exactly that every moving particle has an associated wave. He argued that the wave-like behavior should be linked to the particle's momentum, just as light's wavelength is linked to its momentum. De Broglie's hypothesis was revolutionary because it extended wave-particle duality from light to matter, laying a foundation for quantum mechanics. He presented his idea in his 1924 PhD thesis, Recherches sur la théorie des quanta, and later won the Nobel Prize 1929 for it. De Broglie suggested the wavelength lambda of a particle is given by lambda equals h divided by p, where h is Planck's constant 6.626 times 10 to the minus 34 joule seconds, and p is the particle's momentum. To see where this comes from, start with the relativistic expression for momentum. P equals gamma mv, where gamma equals 1 over the square root of 1 minus v squared over c squared, and m is the rest mass. For a wave, the angular frequency omega and wave number k are related to energy and momentum. E equals h bar omega and p equals h bar k, h bar equals h over 2 pi. For a free particle, the relativistic energy is E equals the square root of p squared c squared plus m squared c to the fourth. Substituting p equals h bar k and solving for wavelength, lambda equals 2 pi divided by k gives lambda equals h divided by p, independent of the detailed form of gamma. In the low-speed non-relativistic limit v much less than c, p is approximately mv, so lambda is approximately h divided by mv. This simple formula works for electrons in a cathode ray tube, neutrons in a reactor, even large molecules like C60 fullerenes, provided we use the correct momentum. Photons are the bridge that connects energy, frequency, and momentum. For a photon, energy is E equals hf, h is Planck's constant, f is frequency, and momentum is p equals h over lambda, because lambda equals c over f. If you rearrange the photon relations, you obtain lambda equals h over p, the same form de Broglie gave for massive particles. The key insight is that both light and matter share the same mathematical link between wavelength and momentum. This shows that wavelength is not a property exclusive to light, it is a universal attribute of any quantum object. For example, an electron accelerated through a voltage v gains kinetic energy eV, so its momentum p equals square root of 2m eV. Inserting this p into lambda equals h over p gives the electron's de Broglie wavelength, which can be compared directly with the photon wavelength for the same energy. When we talk about a wave packet, a localized bunch of waves that represents a particle, two speeds are important. The phase velocity v sub p is the speed at which a single frequency component of the wave, the crests, travels. V sub p equals omega over k. Using the de Broglie relations, omega equals E over h bar and k equals p over h bar, and the relativistic energy-momentum relation, you find v sub p equals E over p equals c squared over v, where v is the particle's ordinary speed. The group velocity v sub g is the speed of the wave packet envelope, calculated as v sub g equals d omega dk. Differentiating the relativistic energy gives v sub g equals pc squared over E equals v. Thus the group velocity equals the particle's classical velocity, while the phase velocity is larger than c for massive particles. Their product is always v sub p times v sub g equals c squared, a neat identity that shows the two velocities are linked but not contradictory. The superluminal phase velocity does not transmit information, so relativity is safe. In quantum mechanics, a particle is described by a wave function psi of x, t. The square of its absolute value, the absolute value of psi of x, t squared, gives the probability density, the chance of finding the particle in a tiny interval around position x at time t. For a free particle with a single wavelength lambda, psi can be written as a simple plane wave. Psi equals a e to the I times open parenthesis k x minus omega t close parenthesis, where a is a constant. To make physical sense, the total probability of finding the particle somewhere must be 1. This gives the normalization condition, the integral from negative infinity to positive infinity of the absolute value of psi of x comma t squared with respect to x equals 1. For bound states, like an electron in an atom, psi is usually a standing wave pattern with nodes, and the constant a is chosen so that the integral of the absolute value of psi squared over the allowed region equals 1. The normalization guarantees that probabilities are properly scaled and allows us to calculate expectation values such as x angle bracket equals the integral of x times the absolute value of psi squared with respect to x. The first convincing proof of de Broglie's idea came in 1927 from the Davison-Germer experiment. Electrons were fired at a nickel crystal, and the scattered intensity was measured as a function of angle. The pattern showed clear diffraction peaks, just like X-rays diffracting from crystal planes. Using Bragg's law n lambda equals 2d sin theta, where d equals spacing between crystal planes, theta equals diffraction angle, the measured angles gave wavelengths that matched lambda equals h over p for the known electron energy, eV acceleration. Later experiments used electron beams on thin graphite foils, producing concentric rings electron diffraction that again obeyed the same wavelength formula. Even neutrons, atoms, and large molecules have shown diffraction, confirming that matter waves behave just like light waves when passing through periodic structures. Consider a particle confined in a one-dimensional box of length L with infinitely high walls, the classic particle in a box problem. The particle's wave function must go to 0 at the walls, so only standing waves that fit an integer number of half wavelengths are allowed. N lambda over 2 equals L, where n equals 1, 2, 3, and so on. Solving for lambda gives lambda sub n equals 2L divided by n. Substituting lambda equals h over p, or p equals h over lambda, into the kinetic energy expression, E equals p squared over 2m yields quantized energy levels. E sub n equals n squared h squared divided by 8m L squared. Thus the allowed energies are discrete, increasing with n squared, and the corresponding wavelengths shrink as the particle's energy grows. This simple model explains why electrons in atoms occupy distinct shells, and why conduction electrons in a metal have specific allowed momentum states. Example 1. An electron is accelerated through a potential difference of 150 volts. Its kinetic energy is K equals EV equals 1.60 times 10 to the minus 19 coulombs times 150 volts equals 2.40 times 10 to the minus 17 joules. The momentum is P equals square root of open parenthesis 2m sub EK close parenthesis equals square root of open bracket 2 times 9.11 times 10 to the minus 31 kilograms times 2.40 times 10 to the minus 17 joules close bracket, approximately 6.6 times 10 to the minus 24 kilogram meter per second. The de Broglie wavelength is lambda equals h divided by p equals 6.626 times 10 to the minus 34 divided by 6.6 times 10 to the minus 24, approximately 1.0 times 10 to the minus 10 meters, which is 0.1 nanometers. This is comparable to the spacing between atoms in a crystal, so diffraction can occur. Example 2. In a Davison-Germer style setup, a crystal has plane spacing d equals 0.215 nanometers. Using the lambda from example 1, Bragg's law predicts the first-order diffraction angle. Sin theta equals n lambda divided by open parenthesis 2d close parenthesis equals 1 times 0.10 nanometers divided by 2 times 0.215 nanometers, approximately 0.233, which gives theta approximately 13.5 degrees. Observing a peak near this angle confirms the wavelength. Example 3. Particle in a box of length L equals 1.0 nanometers. For n equals 1, lambda 1 equals 2L equals 2.0 nanometers. Energy E1 equals h squared divided by open parenthesis 8mL squared close parenthesis equals 6.626 times 10 to the minus 34 squared divided by open bracket 8 times 9.11 times 10 to the minus 31 times open parenthesis 1.0 times 10 to the minus 9 close parenthesis squared close bracket, approximately 6.0 times 10 to the minus 20 joules, which is approximately 0.38 electron volts. For n equals 2, lambda 2 equals 1.0 nanometers, and E2 equals 4E1 approximately 1.5 electron volts. These simple numbers illustrate how the quantization condition forces only certain wavelengths and energies.